Hi everybody, and welcome to the beginning of sections 13.3 and 13.4. And this is page 21 of the workbook that we're looking at. And in these sections, we're going to be looking at two operations that we can do on vectors called the dot and the cross products. Both of these are operations that we'll use often over the course of the semester, and they give us geometric information about how vectors relate to each other that will be very useful for us. Okay, so we're going to start with the first of these two products, the dot product. Okay, so this is called the algebraic definition of the dot product. All right, so we'll start with two vectors in three-dimensional space, v and w, and we're kind of writing those in component notations with I, j, and k. And I don't know if we've mentioned this specifically, but k is just representing distance on the z-axis. We already know that I and j represent distance on the x and the y-axis. Okay, and so here's how we define the dot product. Okay, so first of all, our notation for it is just v dot w, and here's the formula for its calculation. Okay, notice what we're doing. v1 w1 plus v2 w2 plus v3 w3, we're literally just taking corresponding components and multiplying them together. So starting with the first component, we're going to take v1 times w1, and then v2 times w2, and finally v3 times w3, and then just add all of those together. Okay, so let's look at a specific example of actually doing that. Okay, calculate v dot w if v is I plus 2j plus 3k, and w is 3i minus 2j plus k. How would that dot product look? Okay, well, following the formula above, we're just going to take the components and multiply them together one by one. So I is really 1i, so we'll take that 1 and we'll multiply it by 3. That's going to give us 1 times 3 plus, and then move on to the next component, 2 times negative 2. Okay, and then move on to the last component, 3 times the 1 that's sitting in front of the k. Okay, and then just do the arithmetic and see what we get. So 3 minus 4 is negative 1 plus 3 is 2. That's our dot product. Okay, and I want to emphasize here, notice that that dot product is a scalar quantity. It's not a vector. Okay, so one of the interesting things about a dot product is you're starting with two vectors, but what you're winding up with is just a number. It's going to have a magnitude, but not a direction. Okay, and now that we've done an example of calculating a dot product, I want to look at an example that might give us some geometric insight into what's actually going on with a dot product. Okay, so in example 2, they'd like us to calculate u dot v in 3 different situations. All right, and let's start with the first one to the left here. Okay, so they're giving us u equals I plus 2j and v equals 3i plus j. The dot product we would get by just multiplying the corresponding components together, seeing what we get. So 1 times 3 plus 2 times 1, that's going to give us 5. Okay. Okay, and I'd like to just kind of left to right calculate the dot products, and then we're going to come back once we have numbers for all of these 3 and see if we can get some geometric connections going with it. Okay, so moving on to the second picture, here we've got u equals 3i plus j and v equals negative I plus 3j. If we take that dot product, we're going to get 3 times negative 1 plus 1 times 3. That's going to give us 0. Okay, let's maybe separate those from each other. Okay, and then finally over here in the picture to the very right, u is 3i plus j and v is negative 2i minus 2j. That dot product is going to be 3 times negative 2 plus 1 times negative 2. Okay, what would we get if we do that? So negative 6 minus 2 is negative 8. There's our dot product. Okay, and the thing that you might notice as you look at these three numbers, we got a positive number for the first one, 5. We got a 0 in the middle, and we got a negative number for the third one. And it turns out that that positive 0 negative pattern that we're seeing has something to do with the angle between the vectors. Okay, so let's start with the picture to the left and talk about the angle that's between u and v. And notice that that angle is between 0 and 90 degrees. Okay, or in radians, it's less than pi over 2. Turns out that anytime that's true about two vectors, the angle between them is less than pi over 2, you're going to come up with a positive dot product. That will always happen. Okay, and moving on to the second picture, what's the angle between u and v? What does it look like to you? Okay, that looks like a 90-degree angle. Those vectors are perpendicular, and indeed that turns out to be the case. Theta is pi over 2, and anytime the vectors are perpendicular to each other, turns out you're going to get a 0 dot product every single time. Okay, and then finally, in the picture to the right here, okay, this time the angle is actually bigger than pi over 2. Okay, so it's less than 180 degrees, which is pi. And we're getting a negative dot product, and that turns out to also be true in general. If the angle between the vectors is between pi over 2 and pi, you're always going to get a negative dot product.